Building on active fault lines? Yeah, that's a risky endeavor. From towering skyscrapers designed to withstand earthquakes to critical infrastructure built in high-risk zones, join me, I'm counting down 15 structures built on active fault lines. Starting with number 15. The Golden Gate Bridge. It is one of the wonders of the modern world. However, its proximity to the San Andreas Fault, a tectonic boundary between the Pacific and North American plates, makes for a unique history. The Golden Gate Bridge spans the mile-wide strait connecting San Francisco Bay to the Pacific Ocean, linking San Francisco to Marin County. Beneath this iconic structure lies one of the most active tectonic regions in the world. The San Andreas Fault, a continental transform fault, runs just miles offshore. It's known for its right lateral strike-slip movement. This fault has produced devastating earthquakes, such as the 1906 event that leveled much of San Francisco. Now, seismic activity poses a threat to the Golden Gate Bridge. Initial assumptions about the bridge's resilience underestimated the forces that a major earthquake could unleash. Studies revealed that a severe quake could lead to a catastrophic structural failure, particularly at critical points like the 320-foot arch over Fort Point. And recognizing those risks, a $392 million seismic retrofit program was initiated to enhance the bridge's ability to endure any quakes. Engineers used a custom electrohydraulic synchronous lift system to transfer the bridge's load onto temporary supports during construction. Now, these measures were designed to ensure that the bridge could withstand seismic events with minimal or repairable damage. This retrofit included strengthening the bridge's towers, anchorage systems, and suspension cables. Special attention was given to the tower's foundations, which of course needed reinforcement to handle more dynamic forces of an earthquake. And despite initial projections for a 2012 completion, the complexity of the project extended its timeline, reflecting the challenges of retrofitting a historic structure while maintaining its functionality. Now let me take it back a bit. 1906 earthquake with an estimated magnitude of 7.8 caused widespread destruction. More recently, the 1957 earthquake, a magnitude of 7.5, served as a reminder of the constant threat posed by the San Andreas Fault. This seismic retrofit of the bridge coincided with broader efforts to improve the surrounding infrastructure. The nearby Doyle Drive and elevated approach to the bridge was deemed seismically unsafe and replaced by a $1 billion Presidio Parkway project. This new design addressed any structural vulnerabilities, ensuring a bit safer access to the bridge in the event of an earthquake. Number 14. The LAX Airport. Los Angeles International Airport is one of the busiest airports in the world, serving millions of passengers annually and acting as a critical gateway for international and domestic travel. However, its location near the Newport-Inglewood Fault introduces a layer of complexity to its operation. It is situated in an area of high seismic activity. LAX represents a significant case study on how critical infrastructure can coexist with the ever-present risk of earthquakes. The Newport-Inglewood Fault, a 47-mile right lateral strike-slip fault that extends from Culver City through to Inglewood and down to Newport Beach, this fault is capable of producing earthquakes with magnitudes between 6.0 and 7.4. Historical events such as the 1933 Long Beach quake, a magnitude 6.4, have highlighted the destructive potential of this fault, really in areas with dense infrastructure. Now, LAX occupies about 3,500 acres, and it includes extensive facilities such as 4 parallel runways, passenger terminals, and a sophisticated fuel hydrant system. Damage to runways, terminals, or those fuel systems could disrupt operations for extended periods, affecting not only travelers, but also the regional economy. To address those challenges, LAX has implemented a range of measures aimed at reducing earthquake risks. One of the most innovative steps has been the introduction of an earthquake early warning system in collaboration with the USGS Shake Alert program. This system uses sensors to detect seismic activity and provides warnings to airport personnel and passengers. The Shake Alert-based system is part of a larger push by Los Angeles World Airports, the operator of LAX, to make the airport one of the most resilient. This initiative also includes retrofitting critical structures, reinforcing the runways, and adopting earthquake-resistant design standards for new construction. Number 13. The Tokyo Skytree. The Tokyo Skytree, it rises about 2,080 feet above the city of Tokyo, and as the tallest tower in Japan and one of the tallest structures in the world, it serves as a critical broadcasting hub and a popular observation point. But what truly sets it apart is its location near the Sagami Trough, a tectonic boundary known for producing powerful quakes. The Sagami Trough stretches about 210 miles along the eastern coast of Japan, where the Philippine Sea Plate subducts beneath the Okhotsk microplate. Now that convergence creates this immense seismic tension and periodically released in the form of megathrust earthquakes. This region has experienced devastating events, including the 1923 Great Kanto earthquake, which caused widespread devastation. Tokyo and the surrounding metropolitan area, home to over 43 million people, remain vulnerable to future seismic events of similar magnitude. At the core of the Skytree structure is a reinforced concrete shaft that extends to a height of about 1,230 feet. This central pillar provides structural integrity, acting as the backbone of the tower, and below 410 feet, it's rigidly connected to the outer steel framework, while above this point, oil dampers mediate the connection, allowing controlled movement during any seismic activity. These oil dampers are a crucial component of the Skytree's earthquake resistance. Now, these devices function as a sort of shock absorber, dissipating any seismic energy and reducing the vibrations transmitted through the structure. Additionally, it also employs a tuned mass damper system which acts as a counterweight to stabilize the tower during both quakes and strong wind. This system is known as an added mass control mechanism. This shifts the mass in the opposite direction to the tower's motion, maintaining its center of gravity and reducing any structural strain. Together, both these features, the central pillar and the mass damper, can absorb up to 50% of the energy generated by an earthquake. Its resilience here draws on lessons learned from past disasters, blending innovation with necessity. Its engineers carefully modeled potential earthquake scenarios, ensuring that the tower would endure even the strongest of tremors. And this approach underscores Japan's commitment to safeguarding its urban infrastructure and protecting its population, of course. Number 12. Istanbul's Hagia Sophia. The Hagia Sophia, completed in 537 AD, is located in Istanbul, Turkey. It's not just an iconic symbol of culture and religious transformation, but it's also an example of ancient engineering designed to withstand earthquakes. Situated near the North Anatolian Fault, it is one of the most active seismic zones in the world. The Hagia Sophia has endured numerous earthquakes over its 1,500-year history. Now, that fault stretches about 930 miles across northern Turkey, marking the boundary between the Anatolian and Eurasian tectonic plates. This fault line has produced some of the region's most powerful quakes, with notable events recorded in 1999 and earlier centuries. Yet the Hagia Sophia has withstood those natural forces largely due to the advance of engineering employed during its construction and subsequent reinforcements. One of the most significant features of the Hagia Sophia's construction is its massive central dome, which rests on these things called pedentives, or curved triangular sections, that allow the circular dome to transition onto the square base. This architectural breakthrough distributes the weight more evenly, reducing the stress on any single point and allowing the structure to absorb seismic energy. Lightweight bricks and mortar were chosen for the dome to minimize the overall weight of it, and additionally the mortar contains a high lime content, making it slightly flexible and better able to absorb the forces of a quake. Throughout its history, the Hagia Sophia has been subjected to numerous quakes, including severe events in 553, 869, 989, and 1344 AD. Each quake caused varying degrees of damage, but the structure's design and timely repairs ensured its survival. For instance, after the 989 earthquake, it caused a partial collapse of the dome. A renowned architect, Tradat, was commissioned to repair it. He introduced the additional structural reinforcements, including external buttresses, which enhanced the building's stability. Number 11. Tehran Tower. The Milad Tower, also known as the Tehran Tower, is a landmark in Tehran, Iran, and it's a feat of engineering designed to endure in one of the most seismically active regions in the world. Standing at over 1,427 feet, it is Iran's tallest tower and ranks among the world's tallest freestanding structures. The Moshe Fault runs along the southern edge of the Alborz Mountains, a tectonically active region near Tehran. Now, this left lateral strike-slip fault has a history of generating huge earthquakes, posing a substantial risk to Iran's capital, which is home to over 9 million people. Iran's geological setting, situated at the convergence of the Arabian and Eurasian plates, exacerbates the frequency and intensity of any seismic activity. About 90% of Iran is crisscrossed by active faults, making earthquake-resistant design essential for infrastructure. Constructed over 11 years and completed in 2008, the Milad Tower incorporates modern engineering techniques to withstand earthquakes. Its design features several key elements aimed at mitigating the impact. The central core of the tower is made of reinforced concrete, providing structural integrity and stability. Now, this core acts as the backbone of the tower, ensuring that it can absorb and redistribute seismic energy. This flexibility allows the structure to dissipate that energy and reduce the risk of any catastrophic failures. While not publicly detailed, it is likely that a structure of this magnitude incorporates a damping system similar to those in other earthquake-resistant towers. Those tuned mass dampers are devices that counteract swaying by moving in opposition to seismic forces, helping to maintain the tower's equilibrium. Number 10. Quito's Historic Center. The Quito Historic District, a UNESCO World Heritage Site, stands as an architectural hotspot amidst a landscape marked by tectonic activity. It's located on the eastern slopes of Pichincha, an active stratovolcano in the Andes. The district is part of Ecuador's capital city of Quito. While its colonial architecture and rich history attract thousands of people every year, its location on or near an active fault line presents some serious challenges. Quito's tectonic setting is shaped by the subduction of the Nazca Plate beneath the South American Plate. Now, this process happens at a rate of about 7 centimeters per year, and it drives the intense geological activity throughout the region. This dynamic results in frequent earthquakes. Now, the Quito Fault, a reverse fault running north to south, poses a direct threat to the city, while the nearby Palatanga and Chingual faults contribute to the region's seismicity. Earthquake swarms, such as those linked to the Pichincha volcano in 1998-99, and historical events like the magnitude 8.8 earthquake in 1906, underscore the city's vulnerability. The narrow streets and dense layout of the district exacerbate this risk, as collapsing structures could trigger chain reactions of destruction. Retrofitting initiatives have introduced some reinforcements to some buildings, while urban planning has incorporated earthquake preparedness measures. Modern seismic codes govern newer constructions, but the historic district poses unique challenges due to its culture and architectural significance. In addition to any structural adaptations, Quito has implemented community education programs and regular earthquake drills to prepare residents and visitors for any potential disasters. Number 9. California Memorial Stadium. California Memorial Stadium, located on the University of California, Berkeley campus, is a historic landmark with a fascinating geological distinction. It straddles the Hayward Fault. This positioning has made it a subject of engineering and seismic risk management, as the stadium exemplifies the balance between human ambition and the natural forces of an active fault zone. The Hayward Fault is a right lateral strike-slip fault running along the densely populated eastern edge of the San Francisco Bay. It's part of the complex tectonic interactions between the Pacific and North American plates, and the fault stretches about 74 miles, passing through urban hubs like Berkeley, Oakland, and Fremont. Known for its potential to produce significant quakes, the Hayward Fault last unleashed a major quake in 1868, and it remains highly active, with measurable lateral motion of about 1.2 millimeters per year. Over the decades, the gradual creep of the fault has caused visible separation in the stadium's walls, posing challenges for the structural integrity and the safety of its occupants. When the stadium was constructed in 1923, its designers faced a unique challenge: how to build a monumental structure directly atop an active fault line. The eastern section was built onto the hillside, while the western side, with its iconic neoclassical facade, was constructed on flatter terrain. Expansion joints were strategically placed at the fault line, allowing the two halves to move independently during seismic events. Well, despite those safety measures, a 1998 seismic safety study rated the stadium as poor, indicating significant life safety hazards. The finding prompted calls for extensive retrofitting and renovation, leading to a comprehensive $300 million overhaul completed in 2012. This decision to retrofit the stadium rather than relocate it reflected its cultural significance. It's listed on the National Register of Historic Places in 2006. Memorial Stadium serves as a symbol of UC Berkeley's storied athletic tradition. Yet the financial burden of the renovation, coupled with ongoing seismic risks, has sparked debate over whether preserving the stadium in its original location was the best choice. Number 8. The Petronas Towers. The Petronas Towers in Kuala Lumpur, Malaysia, is a pair of 88-story skyscrapers completed in 1998, and for a period it held the title of the tallest buildings in the world. Standing at 1,483 feet, the Twin Towers remained the tallest of their kind, surpassing other notable skyscrapers, including the original World Trade Center towers in New York. Well, despite their iconic status and proximity to one of the world's most active seismic zones, the towers were designed with seismic resilience in mind, ensuring their integrity in the event of nearby earthquakes. Now, while the Petronas Towers are not directly above an active fault, they are situated in a region susceptible to seismic activity due to their proximity to the Great Sumatran Fault System, located off the western coast of Sumatra. The Great Sumatran Fault is a major strike-slip fault zone that accommodates the oblique convergence between the Indo-Australian and Eurasian plates. This fault extends for much of the length of Sumatra, and it's a key part of the tectonic system responsible for the region's high seismic risk. Although the Petronas Towers are located on the mainland of the peninsular Malaysia and not directly atop the fault line, their proximity to the seismic activity of the region required careful engineering. One of the most innovative aspects of the tower's design is the incorporation of a double-decker sky bridge, which connects the two towers on the 41st and 42nd floors. At 558 feet above the ground, this sky bridge is the highest two-story bridge in the world, as it serves as both a function and a structural purpose. The bridge is designed to move independently of the towers in response to wind and any seismic forces. Now, this allows the bridge to flex during an earthquake or any high wind, ensuring it remains intact. The towers themselves are constructed with a reinforced concrete core and a steel structure that provides strength and flexibility. This use of a mixed material approach does enhance the ability of absorbing and dissipating energy from seismic shocks, reducing the potential for structural damage. And the foundations of the towers are anchored deep into the bedrock. That's a common engineering solution in earthquake-prone regions. This deep foundation helps stabilize the tower during ground movement, ensuring they remain upright even in the event of a strong quake. Moving on to number 7, the Hoover Dam. The Hoover Dam is one of the most iconic feats of engineering in the United States. It's located in the Black Canyon of the Colorado River, straddling the border of Nevada and Arizona. Constructed during the Great Depression between 1931 and 36, it serves not only as a critical water reservoir, but also as a powerful hydroelectric plant. Standing 726 feet tall, it holds back the waters of Lake Mead, the largest reservoir in the United States. Despite its seemingly impenetrable structure, the Hoover Dam is built near the Mead seismic fault and other fault zones in the region, prompting engineers to take special care in designing it to withstand any seismic activity. While the dam itself isn't directly built over an active fault, its proximity to fault lines pose potential risks. The MSF is a strike-slip fault that runs along the eastern edge of Lake Mead, which means that it can experience horizontal displacement. This fault is part of a broader seismic network in the region, including the larger faults that contribute to tectonic activity along the boundary between the Pacific and North American plates. Given the proximity, the potential for earthquakes in the region has been a concern for the structural integrity of the dam, as seismic forces could lead to displacement and cracking of the dam's concrete structure. Engineers were mindful of this risk during its design and construction, incorporating some key features to ensure the dam could handle the forces. It takes into both account the seismic risks of the area and the unique forces generated by the weight of the water it holds back. It is an arch gravity dam, which means that it uses massive concrete structures to both resist the water pressure and channel the forces of seismic activity. The dam's concrete is particularly thick at the base, 660 feet, and it tapers to 45 feet at the top, ensuring that it can absorb and distribute seismic forces efficiently. In addition to that robust design, the Hoover Dam underwent significant seismic retrofitting to further enhance its resilience. This process included reinforcing critical structural components such as the dam's foundation and joints to improve their ability to withstand ground motion. Though the Hoover Dam is designed to survive powerful quakes, concerns about its proximity to fault lines have been addressed through engineering innovations. Earthquakes in the region, particularly large ones, could potentially cause significant damage to the dam if not properly mitigated. However, despite the risk, the likelihood of a catastrophic failure of the Hoover Dam remains very low due to its extensive safety features. Number 6. Mexico City Cathedral. The Mexico City Metropolitan Cathedral is not only an architectural and religious landmark, but also an example of human perseverance in the face of geological challenges. It's located on the northern side of the Zocalo, Mexico City's central square. This cathedral stands on top of a complex and sensitive landscape built over ancient Aztec ruins and within proximity to an active fault zone. The site's conditions have profoundly impacted both its construction and ongoing maintenance. The cathedral, a central place of worship for the Catholic Archdiocese of Mexico, was constructed over nearly 2.5 centuries, from 1573 to 1813. It was built to replace the original church erected soon after the Spanish conquest of Tenochtitlan. Key contributions were made by architects like José Damián Ortiz de Castro, who oversaw the construction of the bell towers and dome, and Manuel Tolsa, who made significant changes to the dome and facade, giving the cathedral its current appearance. The first 42 years of construction were dedicated to laying the foundation to compensate for the soft ground. Despite this effort, though, the cathedral was still built over the remains of pre-Hispanic structures, creating uneven foundation conditions that would later become significant concerns. Mexico City is located near the Trans-Mexican Volcanic Belt. Now, this is a region that's known for its activity and seismic potential. The proximity to this fault zone has made the city, and by extension the cathedral, highly susceptible to seismic activities. Earthquakes in the region, particularly in the 1980s and in 2017, have shaken the city and caused damage to many buildings, including the cathedral. But over the centuries, the cathedral has experienced noticeable sinking, which results in cracks in the walls, tilted columns, and some unevenness in the floors. In addition to the naturally unstable ground, the proximity to active faults like those associated with the Trans-Mexican Volcanic Belt heighten any risks of significant events. Well, despite the challenges, the cathedral has been continually reinforced and maintained to counteract the effects of any seismic forces. Throughout the 20th and 21st centuries, engineers have developed various strategies to strengthen the foundation and the structure. These efforts have included seismic retrofitting, which involves the installation of steel supports and tension cables, as well as additional reinforcement to the bell tower and the dome. The aim is to prevent further settling and to protect the cathedral in the event of a quake. And interestingly, the aftermath of the 2017 quake demonstrated the importance of ongoing maintenance. While the damage was relatively limited compared to other buildings in the city, the event prompted a major restoration project. During this reconstruction, workers uncovered 23 lead boxes containing religious relics that had been sealed away since the early 19th century. This discovery highlights the continuous interaction between the cathedral's history and the dynamic environment in which it sits. Number 5. Christchurch Cathedral. Christchurch Cathedral, located in New Zealand, was built between 1864 and 1904. This Anglican cathedral has long served as the seat of the Bishop of Christchurch. However, its location on the South Island near the Alpine Fault Zone has placed it in the path of frequent seismic activity. It's situated in Cathedral Square, a central location in the city that's made it both a cultural landmark and a symbol of the city's history. Now, the Alpine Fault, a major geological feature, runs nearly the entire length of New Zealand's South Island, stretching about 370 miles. The fault is known for its rapid strike-slip movement, with average slip rates of about 1.5 inches per year, and it's capable of producing significant earthquakes, with the last major one happening in 1717 AD. Its history has been marred by repeated earthquake damage, particularly to its spire and the tower. As early as 1881, a stone was dislodged from the top of the spire, signaling the beginning of a long history of earthquake-related repairs. Several damaging events followed, including the 1888 North Canterbury earthquake and the 1901 Cheviot earthquake, both of which caused significant damage. Each time, the cathedral underwent restoration efforts, with the spire being rebuilt. But despite those efforts, the cathedral was vulnerable to seismic forces, and it was starkly highlighted by the devastating earthquakes of 2010 and 2011. The 2010 Canterbury quake caused superficial damage, but the real destruction came in 2011. On February 22, 2011, a magnitude 6.3 quake struck, toppling the cathedral spire and severely damaging the rest of the building. The foundation, which was initially designed with considerations for seismic risks, was unable to withstand the forces of the 2011 quake. Further inspections revealed damage to the pillars supporting the cathedral, and the building's stability was in question. Those two recent earthquakes were not the first to damage the cathedral, but they were certainly the most destructive. Its location on the Alpine Fault Zone has ensured that seismic activity has always been a factor in its construction and its maintenance. While the decision was initially made to demolish the cathedral, a shift in approach saw the building's restoration, with early work beginning in 2019. But one of the primary challenges in restoring the cathedral is addressing the seismic risks that led to its destruction. Its foundation was built in the 19th century. It's not equipped to handle the forces generated by the fault. Engineers have to find a way to stabilize the structure and ensure it can withstand future quakes. Number 4. The Transamerican Pyramid. The Transamerica Pyramid, located in San Francisco's financial district, is an iconic 48-story skyscraper completed in 1972. Its sleek, pyramid-shaped design, standing over 850 feet tall, was a bold departure from the more traditional rectangular skyscrapers of its time. For decades, it was the tallest building in San Francisco and remains one of the most recognizable structures in the city. However, beyond its unique shape, the building's design incorporates critical engineering features to withstand seismic activity that's common in the region. One of the most notable design elements is the building's foundation, which reaches about 52 feet below ground level. This concrete and steel foundation is an impressive 9 feet thick, built to handle the forces of an earthquake. Now, this was achieved through a continuous 24-hour concrete pour, a process that's helped ensure a solid, uninterrupted base capable of withstanding shifting ground. Now, the pyramid shape itself, with the tapering form and narrow footprint, also offers structural benefits. This shape allows for greater flexibility during an earthquake, as the building can sway without compromising any stability. The building's facade, made of quartz aggregate panels, provides a durable surface that contributes to this resilience. Inside, the building features over 3,000 windows, with its unique triangular design allowing for better natural light and unobstructed views. The Transamerica Pyramid was one of the first buildings in San Francisco to be constructed with seismic concerns at the forefront of its design. It was heavily influenced by the local environment, particularly the tall redwood and sequoia trees that dominate the region's landscape. The form of these trees, which are known for their tall, conical shape, was mirrored in the pyramid design. However, over time, the building gained popularity, becoming a beloved symbol of the city. And despite ongoing risks of living near the San Andreas Fault, the Transamerica Pyramid stands as an example of resilience of its engineers and architects, demonstrating that even in earthquake-prone areas, modern skyscrapers can be designed to endure the forces of nature. Number 3. Shizuoka Prefecture. Shizuoka Prefecture, located in the region of Japan's Honshu Island, is a key area both geographically and economically. Spanning an area of over 3,000 square miles, it's got a population of just over 3.5 million people as of 2023. It's positioned along Japan's Pacific coast with a diverse landscape that includes Mount Fuji to the north and a coastline along the Pacific Ocean to the south. However, Shizuoka Prefecture is also located near one of the world's most active earthquake zones, the Nankai Trough. The Nankai Trough is offshore to the south of Shizuoka, and it marks a significant subduction zone where the Philippine Sea Plate is sliding beneath the Eurasian Plate. Some earthquakes, typically reaching magnitudes of 8 or 9, have historically caused devastating damage and loss of life. With a predicted 70 to 80% probability of a massive quake happening within the next 30 years, the risk of a catastrophic event in Shizuoka remains high. The fault beneath this region, known as the Nankai Megathrust, has a history of producing earthquakes every 100 to 150 years. The last significant quake in the region happened on March 15, 2011, with a magnitude of 6.2, though the larger, more catastrophic events are those that originate deeper in the Nankai Trough. Given the region's vulnerability, earthquake-resistant infrastructure has been a priority in Shizuoka. Building codes in the prefecture are stringent, and modern structures, including residential, commercial, and public buildings, are designed to withstand the forces of a quake. These buildings often feature flexible foundations, seismic isolation systems, and reinforced materials that allow them to absorb and dissipate seismic energy. Additionally, the infrastructure, such as bridges and roads, are reinforced to prevent collapse during a quake. The design of these structures reflects the necessity to adapt to inevitable seismic activity in the region, especially with the looming threat of a massive Nankai Trough quake. The Nankai Megathrust quakes have been part of Shizuoka's history, shaping its culture and the development of its infrastructure. For instance, in 1707, the Hoei earthquake, originating from the Nankai Trough, caused widespread destruction in Shizuoka and other parts of Japan. This led to significant advancements in earthquake-resistant construction techniques, which have evolved over centuries. Modern Shizuoka buildings incorporate those lessons with cutting-edge designs that allow them to survive even the strongest of quakes. Number 2. The Akashi Kaikyo Bridge. The Akashi Kaikyo Bridge. This is an infrastructure project linking the cities of Kobe on Japan's Honshu Island with Awaya on Awaji Island, and it stands as a marvel of engineering. Completed in 1998, it held the title of the world's longest suspension bridge for several years, with a span of 6,532 feet. However, its location on or near an active fault line, specifically the Nojima Fault, makes it an even more significant achievement. The 1995 Great Hanshin earthquake, which had an epicenter near Kobe, was directly linked to the Nojima Fault. This earthquake, measuring about 7.3 on the Richter scale, caused widespread devastation. The fact that the Akashi Kaikyo bridge was built across this fault line added a layer of complexity to its design and construction. Japan is a country that's prone to frequent seismic activity due to its location on the Pacific Ring of Fire. They've developed highly sophisticated engineering techniques to address those challenges posed by quakes. In response to seismic threat, the Akashi Kaikyo bridge incorporates several advanced features that allow it to withstand quakes and other forces. The bridge was built using a dual-hinge stiffening girder system. Now, this is a design that allows the structure to flex and absorb the energy from any movement without failing. This system enables the bridge to survive quakes with a magnitude of up to 8.5, well above the expected intensity of seismic activity in the region. The bridge incorporates tuned mass dampers that counteract vibrations in the bridge, helping to stabilize the structure. And these dampers work at the bridge's natural resonance frequency, reducing the impact of oscillations caused by both wind and seismic activity. Each of the two towers that support the bridge stands about 975 feet tall, and the central span that can expand and contract by up to 6.5 feet in a single day due to temperature fluctuations is essential for ensuring that the bridge can handle dynamic forces that it encounters. In January 1995, as construction of the bridge was nearing completion, the Great Hanshin earthquake struck the region. This devastating quake caused the towers of the bridge to shift by a few feet, creating the need to adjust the central span to maintain the integrity of the bridge. Despite the damage to the bridge's towers, though, the primary suspension cables and bridge deck were not substantially affected by the quake, demonstrating the resilience of the bridge's design. In response to the impact of the quake, engineers adjusted the central span by 3.3 feet to accommodate the new positions of the towers. The ability to make these adjustments during the construction process demonstrated the flexibility and foresight of the engineering team, who seemed to be well prepared to address any unforeseen challenges. Number 1. The Bay Bridge. The San Francisco-Oakland Bay Bridge, commonly known as the Bay Bridge, is an iconic structure that links San Francisco with Oakland, California. This bridge is a vital component of the transportation network, carrying about 260,000 vehicles a day. However, the Bay Bridge isn't just remarkable for its size and function, but also for its location, as it stands close to the San Andreas Fault, one of the most active fault zones in the world. The Bay Bridge was constructed in the 1930s, with its first span completed in 1936, and its design was based on the engineering knowledge of the time. The bridge was initially a two-deck structure with separate levels for automobiles and trains. However, its location posed a significant risk from seismic activity due to the nearby fault. On October 17, 1989, the Loma Prieta earthquake, measuring 6.9 in magnitude, struck the Bay Area, causing widespread devastation. The Bay Bridge, particularly the eastern span, was severely damaged. A section of the upper deck of the eastern span collapsed onto the lower deck, causing traffic disruptions and one fatality. In response to the damage from the Loma Prieta earthquake and growing concerns about the bridge's vulnerability, the California Department of Transportation initiated a seismic retrofit program. The retrofit was aimed to improve the bridge's ability to withstand future events. The first phase of retrofitting focused on the western span, which involved strengthening the bridge's concrete supports. Techniques such as installing horizontal and vertical reinforcement bars and adding diagonal box beams to reduce side-to-side motion were implemented. Additionally, the eastern span, which was most affected by the quake, was replaced entirely. The new eastern span, completed in 2013, is a self-anchored suspension bridge designed to be more earthquake-resistant than the original structure. This new design incorporated state-of-the-art materials, including more flexible and seismic buffers that allow the bridge to absorb and dissipate energy. The bridge is also equipped with an advanced monitoring system that detects any shifts or stress that could indicate damage or the potential for failure. Seismic retrofitting costs have been substantial, though, with over $6.5 billion spent on improving the bridge's safety, including the replacement of the eastern span. While this expense has been funded through toll increases and state surcharges, the investment is necessary to ensure the bridge can continue to serve as a critical transportation link between San Francisco and Oakland in the event of another major quake. Thanks for watching, everybody. I'll see you next time. Thank you to our channel members: